Hey everyone, it's time for another super important lesson. Today we're gonna learn how to create and use a new type of data, the pointer. Up until now, we've learned how to create variables, constants, and arrays. A variable is a spot in memory that stores a number. That number can be either an integer or a floating point value. Just a reminder, characters are stored in memory as numbers too. And we also know that variables' value can be changed. A constant is pretty much the same, except you can't change its value. An array is a group of such values, where each item in the sequence has its own index. And now it's time for pointers. A pointer is a variable that stores an address. An address is also a number, an integer, but in C++ an address has its own special type. Every byte in RAM has its own number or index. That number is what's stored in pointers because it's the address of a specific memory location. Let me say it again. A pointer is also a variable, which means you can assign it a value and change it. Lots of things in C++ have addresses: variables, constants, variable arrays, constant arrays, functions, and even pointers themselves, because they're variables too. And that means they're stored somewhere in memory. And that spot in memory also has its own address. So you can create pointers to variables, constants, arrays, functions, and even to other pointers. I'll show you all of that in this lesson. But first, you need to learn how to get the address of all this stuff. To do that, there is a special symbol called the ampersand. That's this symbol. You get it by pressing Shift+7. You just put it in front of the data and it gives you its address. For example, I've created all the types of things you already know that have an address: a function, a variable, a constant, a variable array, and a constant array. They all exist somewhere in memory, so they all have an address, which means we can get it. Below, I'm printing out the address of each one. Notice how I placed the ampersand in front of every name. That gives us the address and we can see it on the screen. Let's run the program and check the output. There's something we need to explain here. Yes, that weird-looking set of numbers is actually the address of that data. Every number you see is being printed in hexadecimal. That's a base 16 number system, which includes not just digits but also letters. I'll talk more about this and other number systems in a future lesson. But for now, just remember, it's just an integer. Why does it show up in hex? Because when you send an address to cout, it's set up to print it in hex by default. But we can turn that address into a regular number. We just need to cast it to an integer type. The best choice is long, since the address might not fit in a regular int. Let me run it and show you. I cast only the variable and constant addresses to long, and here's something interesting. The difference between their addresses is 32. Our variable is placed first on the stack. It's an int, which takes up 4 bytes or 32 bits. Right after that, we create a constant, and you can see it really is placed right after the variable in the stack, since the difference is exactly 32 bits, and all the other stuff comes after that in memory. Now let's move on to arrays. This part's a little more detailed. First of all, I mentioned before that the address of an array is the same as the address of its first element. Second, I also said that just the name of the array is already its address. So you can get the address of an array in 3 ways: using the ampersand, using just the array name, or using the ampersand with the 0th element of the array. Either way, you'll get the same address. The same goes for the constant array. Now let's talk about the function. The function's name is its address, so you can use the ampersand to get the function's address or just use the name itself. Just keep in mind, this is not calling the function because we're not using parentheses. It's just the name. That's why the address prints out the same in both cases. Let's move on to array elements. You can prove to yourself that they're placed in memory one after another by printing out their addresses. That's exactly what I did, and when we cast those addresses to long, you'll see the difference between them is also 32 bits. And finally, let's look at strings. They're a bit special. From previous lessons, you already know that cout can't print array elements directly, but there's an exception for strings. That's why when we try to print our string array, it doesn't show the address. It prints the contents of the string instead. So how do we actually get the address of a string? Easy, just use the ampersand with the name of the string or with the 0th element of the string. An address is a special kind of value, and since it can be stored in memory, that brings up the question: how many bytes does an address take up in memory? In C++, the size of an address depends on the platform architecture your program is being compiled and run on. Typically, on a 32-bit architecture, x86, an address takes up 4 bytes, or 32 bits. On a 64-bit architecture, x64, an address takes up 8 bytes, or 64 bits. See that x64 label up top? That's where you can change your program's architecture. If you want to build 32-bit programs, just switch that to x86. But since 64-bit is a standard nowadays, I'll be using x64. In that case, all pointers, no exceptions, will always take up 8 bytes. Remember that. By the way, you can check the size of an address yourself right in your code. Just write this simple line and you'll see the number of bytes. You do still remember the size of operator, right? Alright, now let's move on to pointers. We'll start with the simplest kind, a pointer to a variable. The syntax is pretty straightforward. You write the variable's type, then the symbol I like to call the asterisk, then the name of the pointer and end it with a semicolon. You can also initialize the pointer. The syntax is just like initializing a variable. You can use the equal sign, curly braces, or both. When it comes to pointers, it doesn't really matter. I personally prefer the equal sign. It looks cleaner and more familiar. An uninitialized variable usually holds garbage. For normal variables, that's just some random number, but for pointers, it's a random address. That could be part of your program or someone else's, so be careful when working with them. Now about the asterisk. You can put a space before it, after it, or leave it without any space. I like writing it next to the type. Some people prefer putting it next to the pointer name. Visual Studio often formats code with the asterisk on the left. In the examples below, I created a variable and showed how you can assign its address to a pointer. And since a pointer is a variable too, I later created another variable and give the pointer a new value. So yeah, a regular pointer can point to different addresses. You can't assign random numbers to pointers. Like here, I'm trying to assign the number 200 to a pointer. The compiler throws an error because a pointer needs an actual address. But you can assign one pointer to another as long as they're the same type. Otherwise, you'll get an error. Like in the next line, the pointer on the left is for double and the one on the right is for int. You might think, why is that a problem? They're both addresses. Well, the thing is, we don't specify the type in a pointer just for fun. The reason is you can actually access the variable through the pointer. See above, we have an int variable. It holds a value and that value takes up 4 bytes of memory. Then we have a pointer to that variable. It stores the address. But how can you work with a variable through just the address of its first byte? How does the program know how many bytes belong to that variable? That's what the pointer's type tells it, int. So the program knows to grab 4 bytes when working with this pointer, but if the pointer is a double, then it would try to use 8 bytes. That's why we get an error here. Now you might ask, but float is also 4 bytes, so can I assign an int address to a float? Still no. That's because the type doesn't just say how many bytes to take, but also how to interpret those bytes. Even though in int and float both use 4 bytes, the way those bytes are stored and read is different. And maybe you were also wondering earlier, if all pointers just store addresses, why do we even need to give them a type? Well, there's your answer. The data at those addresses can be different types and each one is handled differently, so the pointer needs to know the correct type. See how it works with pointers, so you can print a pointer's value with it. Just remember, the value of a pointer is the address of the variable it points to. It doesn't point to the value itself, it points to the address. And again, the value of the variable is 100. The value of the pointer is the address of that variable. So when we print it, we'll see the address. Alright, so now we know how to create basic pointers. But why? Right now, we don't really know why we need these variables. They seem kinda useless, but here's the thing. We can actually look inside the address stored in a pointer. That's called dereferencing a pointer. It's when you take an address and get the value that's stored at that address. To dereference a pointer, we also use the asterisk symbol. Take a look at this example. I created 3 variables of different types. Then I made 3 pointers, each pointing to one of those variables. Next, I printed out the values of those variables in 2 ways. First, using the variable names, and then using the pointers by dereferencing them. Notice, you place the asterisk in front of the pointer name. That tells the program, give me the value stored at the address this pointer holds. Let's run the program and see. We get the same values both ways. So now you can not only work with variables directly, you can also work with them through pointers. In the next 3 lines, I created 3 more variables, and using the pointers from earlier, I assign new values to these new variables. For example, in the first line, I dereference a pointer, get the value 1, add 10 to it, and store the result in a variable named d. The next line is more interesting. There, I take the value that ptrb points to and multiply it by itself. Now remember, the asterisk on the left of a pointer means dereference, but the asterisk between 2 values means multiplication. And in the third line, I take the character value pointed to by a pointer, subtract 2, and then add 5. The result is the character f. But when you dereference a pointer, you're not just getting the value of a variable, you're actually getting the variable itself. Think of it like this. Anywhere you dereference a pointer, it's as if you wrote the variable's name directly. That's why this line works. On the left side of the equal sign, it's not just the number 1, it's the actual variable, and you're changing its value to 50. You're not changing the pointer's value, which is the address. You're changing the variable's value through the pointer. And when I print that variable again, we'll see the new value. Let's run it. Now, one pointer can work with any number of variables as long as they're the same type. Like here, I assign the variable d to the pointer ptra. Before, it pointed to a, now it points to d. And I use that pointer to change the value of d and print it. Let's run that too. So what's the takeaway so far? With pointers, you can work with data. You can store their addresses, access their values, and even change them. But you're probably wondering, why should I even bother with this when it's easier to just use the variable directly? That answer's coming at the end of the lesson. Hang in there. And finally, you should understand that in this last line, I'm not creating 2 pointers. The asterisk belongs only to the first name. So here I'm creating 1 pointer and 1 regular int variable. If you want to create multiple pointers in one line using commas, you have to put an asterisk next to each name. This whole time, we've been creating pointers to variables, but you can also create pointers to constants. See, constants actually have a different type than regular variables. In the next example, I made a variable and a constant. Then I created a pointer to the variable and a pointer to the constant. Notice how I added the word const before int. So you read it like this: pointer to a constant of type int. Also notice I don't have to initialize it right away. The pointer itself is not a constant. It points to a constant, but it's still just a regular variable. I can assign it different constant addresses at any time. Let's keep going. I take the pointer to a variable and assign it the address of a variable. That works fine, makes sense. But the next line gives us an error. You can't assign the address of a constant to a pointer to a variable. Why? Because you already know that with a regular pointer, you can change the value of the variable it points to. And if this line were allowed, you'd be able to change the value of a constant through a pointer, and that breaks the whole idea of a constant. So pointers to variables can only point to variables. In the next few lines, I take a pointer to a constant and assign it the address of our constant. That works just fine. Totally logical. Constant on the right, pointer to constant on the left. But here's something interesting. You can assign the address of a variable to a pointer to a constant. Why is that okay? Because nothing is being broken here. The idea is when you use a pointer to a constant, you're not allowed to change the value it points to. So if you give it a variable's address, it just treats that variable like a constant, meaning you won't be able to change the value through the pointer, but you can still change the variable itself directly, like normal. Below that, I'm showing that using pointers to constants works just like regular pointers. Here's how you print the value of the pointer. Remember, that means the address it stores. Right now, it's holding the address of a variable, so the two addresses should match. Next, I show that you can change the value of a pointer to a constant because the pointer itself is still just a variable. Then I print its value and it should match the address of the constant now. Let's run it and check. And finally, you can also dereference a pointer to a constant to get the value of the constant. Let's run that and see. But like I said earlier, you can't change the value that a pointer to a constant is pointing to. Even if it's pointing to a regular variable, in both of these lines, you'll get a compile time error. Now, let's move on to pointers to arrays. We'll start with an array of variables, or a regular variable array. I created a constant for the array size, and then the array itself. So how do we create a pointer to it? You can use the exact same syntax as with pointers to variables, like this for example. I already told you a few times that the name of an array is the address of its first element, so you can just use the array's name to assign it to the pointer. Or you can directly use the address of the first element, like here. So what does this do for us? Now you can work with the array through the pointer, and it'll behave exactly the same. Here I print all the elements of the array using the array name, and here I print them using the pointer. Yep, you can use indexing with the pointer too. Why that works, we'll talk about later. When you run this, you'll get the same number of elements with the same values. Let's run it and see. So here, the pointer is basically like an alias for the array. But the pointer can also be pointed to a different array, like I did here. And notice, the pointer can point to arrays of any size. But technically, this is not a pointer to an array. It's still a pointer to a variable, and we can prove it. We can prove that. Look at the line 26. Here I try to take the address of the array and assign it to the pointer, and we get an error. Why? Didn't we already see earlier that the array name, the address of the first element, and ampersand with the array name all give us the same address? So what's the problem? Well, the issue is the type of an array is different from the type of a variable. If you have a variable of type int, its type is just int. But if you have an array of ints, its type is int square bracket. That's the difference, the square brackets. And when you use just the array name, you're getting the address of the first element, which is of type int asterisk. But when you use the ampersand with the array name, you're getting the address of the whole array. The address may look the same, but the type is different. It's int square brackets. That's why this line fails. So if you actually want to create a pointer to an array, not just the first element, you need to use the specific syntax. First, write the type of the array's elements, then open parentheses, put an asterisk and the name of the pointer inside. Close parentheses and then add square brackets with the array size. That size has to be either a constant or a literal. You can't use variables there. Below, I show an example of how to create such a pointer. In our case, this is a pointer to an array of 5 elements, which means you can't assign it the address of an array with 6 or 4 elements, only 5. Why do we need the parentheses here? They set the priority. If you take them out, you're not creating a pointer to an array anymore. You're creating an array of 5 pointers to int. We'll cover that kind of data later in a separate section. Now, here's the catch. If you really create a pointer to an array, you won't be able to use it the same way you use a pointer to a variable. If you try to print all the elements through this pointer, you'll see this. It prints addresses, but why addresses? Why is the compiler underlining this line? Well, the program looks at the type of the thing you're indexing. If it's a regular array or a pointer to a variable, like in the earlier example, it works as expected. So if you write square brackets 0, it shows the first element. Square brackets 1 gives you the second, and so on. But if it's a pointer to an array, the problem thinks square bracket 0 means give me the address of the whole array. Square brackets 1 means give me the next array after that, and so on. That's why you see addresses, not of the array elements, but memory regions starting at your array and then jumping ahead by the array's full size in bits. That size is 32 times 5. Why? Because int is 32 bits and there are 5 elements, so the distance between addresses is 160 bits. So if you want to create a pointer for working with an array, just use a pointer to a variable and assign it like this, not like that. But you might ask, so when do we actually need to use that complex syntax? Well, there are a few situations, but they're pretty rare. For example, when you're passing a 2D array from the stack to a function, or when you want to write a function that only accepts arrays of a specific size. If you go study pointers from other sources, in like 99% of them, I'm pretty sure you'll hear or read that a pointer to an array is created this way. But I just showed you that this is actually still just a pointer to a variable. People might call it a pointer to an array just because you can use it to work with arrays. But technically, a real pointer to an array looks like this. Still, I'll keep calling the simpler version a pointer to an array, just because it's more convenient and easier to remember. Now let's talk about pointers to constant arrays. First, let's get the terminology straight. In C++, there is no such thing as a variable array as a concept, because that would mean an array that can change its size. It's more accurate to say array of variables, meaning each element in the array is a variable. Same with constant array. What people usually mean is an array where the elements are constants. But technically, all arrays in C++ have fixed size anyway, so it makes more sense to say array of constants, meaning each element is a const. Still, people often say variable array or constant array and mean exactly that. So whenever I use these terms in this lesson, know that when I say variable array, I mean an array of variables, and when I say constant array, I mean an array of constants. Got it? Alright, let's move on. You already know how to create a pointer to a variable and a pointer to a constant. And you know that a pointer to a variable works just fine with a variable array. But what about a constant array? Well, the situation is pretty much the same. Let's look at the code. We've got two arrays, one with variables, the other with constants. And we've got two pointers, one that can point to a variable and one that can point to a constant. Now look at the next two lines. I try assigning the array addresses to the pointer to a variable. When I try doing that with the constant array, it doesn't work. Why? Same reason as with regular constants. If this were allowed, you could change the values of the constant array's elements through the pointer, and that breaks the definition of a constant. Now check the next two lines. This time we do the same thing, but with the pointer to a constant. Everything works fine. You can use a pointer to a constant with both a variable array and a constant array. You just can't change the values of the elements through that pointer. By the way, maybe you're wondering, when we work with regular variables through pointers, we have to use the asterisk to dereference the address. But when we work with arrays, we don't use it. Why is that? Well, it's because the indexing operator, those square brackets, is what's called syntactic sugar. When you write code like that, the compiler secretly shifts the address by the given number of elements and then dereferences it automatically. I have a timestamped section in this lesson called Why Does Array Element Index Start from 0 in C++. I'll explain all the details there, but for now, let's keep going. We've got a pointer to a variable, check. A pointer to a constant, check. A pointer to an array, check. So what else can we point to? Another pointer! Like I said earlier, pointers are just variables, and variables live in memory, which means they have an address. So you can grab that address and store it in a pointer too. Now, I'm sure some of you are getting a little frustrated, asking yourself, why the hell do I need all this crap? I don't see the point of these dumb pointers. A pointer to a pointer? Really? Why? Don't worry, I'll answer all of that. Just stick with me. Let's look at an example. We've got a variable and a pointer to that variable. So how do we create a pointer to that pointer? Here's the syntax. All you do is add one more asterisk. And here's an example. How do you read it? Read the line from right to left. First, you see the name. Okay, so that's some data. Then the next thing is an asterisk, so it's a pointer. But what kind of pointer? Next, you see another asterisk. That means it's a pointer to a pointer. But a pointer to what? To int. So this is a pointer to an int. Now, through that, you can work with both the inner pointer and the variable it points to. For example, here are three ways to print the value of a variable: directly by its name, by dereferencing the normal pointer, and by double dereferencing the pointer to the pointer. Why double? Because when you dereference the pointer to pointer once, you get the value that it stores, which is the address of the regular pointer. So if we look at it backwards, what does the pointer to pointer hold? The address of another pointer. If we dereference it once, we get that pointer, and if we dereference that, we get the value of the variable. That's why all three ways print 10. Let's run it and check. Let's go further. You can also print the address of a variable in three ways: using the ampersand with the variable name, using the value stored in the pointer to it, or by dereferencing the pointer to pointer once. All of them give you the same address. Let's run it and check. Back up a bit. How do we get the address of the pointer to the variable? Easy. Either use the ampersand with the pointer's name, or use the value stored in the pointer to pointer. Same thing. Let's run it and check. And of course, the pointer to pointer itself also have an address. In fact, all the pointers we've created so far are stored on the stack because they're just regular local variables. To get that address, just use the ampersand with the name of the pointer to pointer. By the way, you can also create pointers to pointers to pointers. You can go as deep as you want. The only difference is the number of asterisks you need to add. And yes, through a pointer to a variable, you can change the actual variable, just like I did here. I double dereference the pointer to pointer, reach the variable's value and change it. Then I print the value of the variable and we see that it really did change. Finally, let's talk about constants. Here we've got a constant and a pointer to that constant. If you want to create a pointer to that pointer, you need to put the word const on the left side too. If you leave it out, you'll get a type mismatch error. Let's keep exploring the fascinating world of pointers. Now we're moving on to function pointers. Just a quick reminder. The name of a function is actually its address in memory. So if you want to get the address of a function, you can either just use its name or use the ampersand with the name. In this case, it makes no difference. So how do we create a pointer to a function? A function has two things that define its type: the types of its parameters and its return type. So when you want to create a function pointer, you have to specify both. First, write the return type of the function. Then open parentheses, put an asterisk, and write the name of the pointer. Close the parentheses and then open another set. This second set is for the parameter list. If the function has no parameters, you still need to include the empty parentheses. If it has one or more parameters, you have to list the types of each one, separated by commas. No need to write the names of the parameters. At the top, I've created 4 functions. The first one doesn't take any parameters and doesn't return anything. I made a pointer to it. It looks like this. Right now, that pointer doesn't point anywhere, but it can point to any function with the same type. In the next line, I assign it the address of the function. And again, you can use the ampersand or skip it. Now look at the other functions. Each one has a different type. The second one takes 1 parameter, the third takes 2, and the fourth one also returns an int. Now look at how I create pointers for each of them. For the first 2, I include the parameter types. Note the array type has those square brackets, and in the last one, I start with int instead of void because that's the return type. Now, you can call functions through pointers. Below, I call a function in 3 ways. The first is a normal function call, nothing new there. The second is calling it through the pointer. Just add parentheses to the pointer to call it. You can think of it like the pointer's name is temporarily replaced with the function's name. The third way is basically the same as the second, but this time I'm dereferencing the pointer first. Why? Well, you might be thinking, if we always dereference pointers to get the actual data, shouldn't we do the same here? But a function isn't data. Its address points to the beginning of its code. In C++, these 2 ways of calling the function are identical. If you want to dereference the pointer first and then call it, go ahead. But honestly, I almost never see that in real code. Calling the function directly through the pointer like this is just cleaner and easier to read. You might also wonder, why the extra parentheses? If you leave them out, the compiler thinks you're calling the function first and then trying to dereference whatever value it returns. And yes, functions can return addresses. I'll show you how that works later. Let's keep going. We've already learned how to create regular pointers to data and functions, but now let's talk about constant pointers. This is not the same as a pointer to a constant. A constant pointer is like a regular constant. It's a variable that holds a value, in this case an address, and that value can't be changed. So once you create a constant pointer, it gets tied to one address and can't be pointed anywhere else after that. but you can still create a constant pointer to a variable or to a constant. Let's look at some examples. I created a regular function, 2 variables and 2 constants. Then I made a pointer to a variable and a pointer to a constant. You already know how those work, but both of those pointers are regular variables. You can assign them one address, then another, and another after that. So how do you make a constant pointer? You need to write the word const after the asterisk, not before. Everything else stays the same. Look at the next line. Here I try to create a constant pointer, but we're getting a compile time error. That's because this pointer is a constant and it doesn't have a value yet. We need to give it one. In the next line, that's what I do. I create a constant pointer to a variable and assign it that variable's address. In the line after that, I try to change the pointer's value and I get an error. That's because it's a constant and you can't change it. But you can still use the pointer to work with the variable. Here, I print the variable's value to the screen. Here I change the value through the pointer and then I print it again. Let's run it and take a look. Now, I create a constant pointer to a constant, but I assign it the address of a variable. So what does this mean? First, the pointer can only point to that variable. Second, you can't change the variable's value through this pointer. That's why we get an error here and here. All you can do is read the value through the pointer. It works the same with arrays and functions. Here I create an array of variables, and here and again here I create a constant pointer to that array. And in the last line, I make a constant pointer to a function. That means it'll always point to that one specific function. Since pointers are also data, we can create arrays of pointers. The syntax looks like this. Write the data type, then an asterisk, then the name of the array, and finally the size in square brackets. At the top, I created an array of pointers to variables. Using list initialization, I assign each element in the array the address of a different variable. You can do it like this, or like the example shown below. Then I print out the value of each variable using the array elements, which are pointers. You can also create arrays of pointers to constants, arrays of constant pointers, arrays of function pointers, arrays of constant pointers to constants, etc. Remember how if you don't give a variable a value, it just holds garbage. Same goes for pointers. Here's an uninitialized pointer and it holds some random address. You can still dereference that pointer and even try to change the value it's pointing to, but most likely you'll get a runtime error because you're accessing memory that doesn't belong to you. That's why pointers are usually kept in one of two states. Either they point to valid data or they don't point anywhere at all. In other words, a pointer can be set to null. There are 3 ways to do this. You can assign it 0, use null, or use nullptr. There is no difference in how they behave. But let's go through the history real quick. Back in the C language, you could just assign 0 to a pointer. That meant it was a null pointer, one that didn't point to anything. But the problem was regular variables could also hold the value 0, so it wasn't always clear whether something was a pointer or just a number. To fix this, they created the null macro. If you've already seen randmax before, that's also a macro, basically just a name that gets replaced with a value. So null just gets replaced with 0. It's literally the same thing. That's why many programmers started using it. In C++, we got a special keyword, nullptr. What's the difference between that and just using 0? Honestly, the full answer probably won't make sense yet. You're not quite ready, but I'll still give you a basic idea. First, nullptr is a null pointer with a specific type, std nullptrt. Also, nullptr isn't a number. It's a type safe pointer. That means it makes your code safer, clearer, and easier to read. How exactly? I'll explain later once we get to the part about pointers as function parameters. Either way, I recommend you use nullptr. Why do we need this at all? So we can check whether a pointer is empty or actually pointing to something. For example, like this, you can compare it to 0 or nullptr, or even just write the pointer itself in an if statement. If the pointer is null, its value is 0, which counts as false in an if. And only when the pointer is not null should you try to dereference it. Why does this matter? Well, in the future, you'll see a lot of code that works with pointers. Some functions will accept pointers, some will return them. Some tools will allocate memory and store the address in a pointer. Others will free the memory and reset the pointer to null. For example, imagine you write a function that creates a character on a heap and returns the address, so you can use it through a pointer. But if there's not enough memory, the function returns nullptr, and that gets stored in that pointer. Then you can check. If the pointer isn't null, that means we've got a character and we can work with it. Alright, let's move on. Next up, the void pointer, a pointer that can point to any type. Sounds cool, right? First question that pops up, well, then why do we even need pointers to specific types if we've got this more powerful one? But here's the deal, it's not actually a better version of regular pointers. Sure, a void pointer can store the address of any object, but it can't be dereferenced directly. That's because the compiler doesn't know how many bytes to read from memory. Let's take a look at an example. We have a variable, and then we create a void pointer that points to it. Now it holds the variable's address. But if we try to see what's at that address through this pointer, we can't. Because it's just the address of the first byte, and the pointer doesn't know how many bytes make up the full variable. That's why C++ won't let you dereference it directly. But here's the workaround. You can cast the void pointer to a pointer of the correct type, like we do in this example. Once it's cast to the right type, that new pointer can be safely dereferenced. So where do void pointers actually get used? One common place is in standard C library functions, for example the std_malloc function. We'll get to it eventually. It returns a void pointer. So yeah, these pointers pop up more often in C than in modern C++. Bottom line, void pointers are powerful when you need something flexible, but they require careful and safe casting. They're useful in low-level programming, but in modern C++, they're used less often thanks to better tools like std_variant or std_any. Don't worry, we'll get to those too. Let's keep going. Now we're gonna look at pointer arithmetic. That's a set of operators and operations you can use with pointers. Pointer arithmetic is one of the most important parts of working with pointers in C++. It lets you move around in memory, especially handy when working with arrays. I'll show you an example right away and explain as we go. We've got an array. I made a pointer to its first element. Now I want to print the addresses of all 5 elements. I can do that like this. I take the address the pointer is holding and add an integer to it. Notice, I'm not dereferencing the pointer, I'm just adding the number to the address. Let's say the address of the first element is 100. If you add 1 to that address, it's not 101. Because with addresses, you're basically adding number of cells or offsets, not just raw numbers. Since each element is an int, you're adding 4 bytes, then 8 bytes, then 12, and so on. So you can think of this line as take the address of the first element and move it to 1 element forward. That way you get the address of the next element. Let's go further. Once you get the address, you can dereference it. Like here, for example. Why did I use parentheses? Because if I leave them out, due to operator precedence, it'll dereference first and then add 1 to the value of the element. And here's a little secret. This is exactly what's happening when you use indexing. Indexing is just syntactic sugar. this code actually turns into that one. And now you can finally understand why indexing starts at 0 in C++, because when you write 0, you're taking the address of the first element and shifting it 0 positions, meaning no shift at all. Alright, moving on. You're not limited to adding numbers to addresses. You can subtract too, like here. I made a pointer to the last element of the array and subtracted different numbers to print the array in reverse order. You can also subtract one address from another. In that case, you get the number of elements or cells between them. Subtraction only works with pointers of the same type. We've got a pointer to the last element and one to the first. Now, how many elements are between them? 4. Why not 3? Because we're looking at the starting addresses of those elements, and if you draw out a layout showing all the bytes of the elements, you'll see that there are exactly 4 elements in between. Look, 1, 2, 3, and 4. The result of subtracting 2 pointers has a special type called std_ptr_diff_t, which stands for pointer difference type. It's basically a type alias for long. Let's print it out and you'll see the number 4. You can also use increment and decrement on pointers. In that case, their values go up or down by 1 element, not by 1 byte. Here I made a pointer to the first element of the array, and I keep dereferencing and incrementing it to move through the array. I can use either the prefix or postfix form. Same goes for decrement. I moved 2 elements back. So what can't you do with pointers? First, you can't do anything with 2 addresses except subtract them. It just doesn't make sense otherwise. Second, you can't add or subtract a floating point number from a pointer. Again, it doesn't make sense. But you can use these operators with bool or char values because they'll just convert to integers. Also, you can't add or subtract numbers with a void pointer because the compiler doesn't know how many bytes to shift by. Here's an example I wrote below. You'll probably see this a lot in real-world programming. There are many situations where you have a sequence of elements, like array, and you make a pointer to the first one, then a pointer to the address after the last one, you could say the end of the sequence, and a pointer to the current element. Then, to go through the sequence, you write a loop that checks whether we've reached the end yet. Keep in mind, that's not the address of the last element, it's the address just after it. Inside the loop, you do something with the current element and then move the pointer to the next one. When we get to STL containers and iterators, the code there will look a lot like this. Let's keep going. An array and a pointer are actually pretty similar. Here's an array and here's a pointer to its first element. You can get the address of the first element either through the pointer or by using the name of the array. You can dereference the pointer to get the value of the first element, or you can even dereference the array name. You can use indexing with both the pointer and the array. You can also add or subtract integers to a pointer or the array name, and you'll just get the addresses of neighboring elements. You can change elements in the array either through the pointer or directly through the array, like this. But there's one thing you can do with the pointer that you can't do with an array: use increment. That's because the pointer is a variable and the array name always points to the first element. It can't be moved. Let's move on to the next topic. You can add pointers as function parameters. Let's look at a function that takes a value and changes it to 10. Now, let's check out the main function. It has a variable and a constant. Then I pass my variable into the function and print its value afterward. If you haven't been paying close attention in my earlier lessons, you might think this function should change the value of the variable, but it doesn't. Let me remind you why. You're passing the value of the variable into the function, in this case the number 20. Then the function creates its own variable, which gets set to 20. The function changes its own variable to 10. When the function finishes, its variable is destroyed, and our original variable still holds the value 20. So how do we write a function that actually changes our variable? It's simple, just pass its address. But to do that, the function needs to take a pointer as a parameter. Here, I made a function where the parameter is a pointer. Inside that function, we dereference the pointer and change the value at that address to 10. In the main function, I call this function and pass the address of the variable, not its value. The function will create its own pointer, which stores the address of our variable. It changes our variable, then the function ends and the pointer goes away. But our variable will now hold the value 10. Let's run the program and see what happens. But notice, our function takes a pointer to a variable as a parameter. That means you can't pass it the address of a constant, like I'm trying to do here. Now onto arrays. You already passed arrays into functions before, and you've written code like this. What's really happening is that a pointer is being created. So these two syntaxes are actually identical. That means when you use square brackets, you're still creating a pointer to a variable, or a constant in this case. Now let's look at the main function. It has an array and we're passing it into a function. But how are we doing that? We're writing its name, and the name of the array is the address of its first element. So that address gets stored in the pointer parameter of the function. That's why you were able to modify elements of the array by passing it to a function, because you were always passing its address. And you'll go even further. You could even pass the address of a regular variable instead of an array, but that would probably lead to runtime errors. Also, since it's just a pointer to an address, you're not limited to passing the address of the first element. You can pass the address of any element like I did here. That way, the function will print the last 4 elements. Sometimes, you might want to write a constant pointer parameters in your functions as a way to protect yourself from accidentally changing the pointer value. Personally, I've never written code like that, and I've never made mistakes because of it. I've also never seen other programmers write const pointers as the function parameters. Maybe it's just extra protection that isn't really needed. But if you want to, go ahead. Also, we've got a function called initialize, and its first parameter is a pointer to a variable. That's why you can't pass an array of constants to a function like that, only an array of regular variables. Now, let's get back to nullptr. We've got an overloaded function. The first version takes a number and the second one takes an address. So which version do you think gets called? The first one, of course, because 0 is first and foremost a number. And what if the programmer meant to call the second function? We know that pointers can also hold the value 0, right? That's the problem. And it's solved by using nullptr, because nullptr is definitely a pointer. It can't be interpreted as a number. So when you use it, the second version of the function gets called. That's why you should use nullptr instead of 0 or null. Let's keep going. Up to this point, our functions could only return numbers, or maybe characters for bool values. Now, we're going to learn how to return addresses from functions. Take a look at this first function. It returns an address to an int. Inside, we create a variable and immediately returns its address. In the main function, I call that function and it returns the address. We store that in a pointer and print the value. So what happens? According to the C++ standard, this is undefined behavior. Why? When you call the function, it creates a variable on the stack. When the function ends, the variable is destroyed. So now we're returning an address that points to memory we no longer own. That address goes into our pointer and we're trying to read from it. If I run this code on my machine, I might still see the value 10. Why didn't I get a runtime error? Maybe the memory just wasn't cleared yet, but you should never write code like this. Your pointers must point to a valid memory. So let's look at the second example. Here's a function that takes an array, finds the largest element, stores its index and returns its address. We can return it like this or like that, it doesn't matter. In main, we have an array, and its biggest element is the one with the value 30. I call our function and store that address in this pointer. Now we can use the pointer to access the max element. For example, I changed its value. Then I print the array value again, and instead of 30, I'll see 500. This is a good example because our function returns valid memory. The array exists in main, which means it's there before and after the function call. But take another close look at the function. It doesn't change any of the elements in the array, so you might ask, should we add const to the parameter? Sounds reasonable, it protects from accidental changes, but then we get an error. The reason is, now the parameter is a pointer to a constant and you're trying to return a pointer to a regular variable, basically removing const, and that's not allowed. So you'd also have to add const to the return type. If you're returning a pointer to a constant, then you need to receive it as such. But now there's an error in the main function. We're assigning that address to a pointer to a variable. To fix this, we also have to add const to that pointer. But now we can't change the value through the pointer. So what do we do? Two options. Either accept that we shouldn't use const at all in this case, or create an overloaded function that only works with const. Let me quickly write it up. The top function will get called when we pass in an array of variables, and the bottom one when we pass in an array of constants. Let's look at the third example. Straight to the function. It takes a number for a day of the week, checks it, and returns the name of the day. It's a string, so we return a const char asterisk. Why not just char asterisk? Because string literals are constant arrays. Only a pointer to a constant can point to them. Now, you might be wondering, don't we get the same issue here, returning a pointer to memory that's already gone once the function ends? If you paid close attention in the last lesson, you know that string literals live in static memory and they stay there for the entire time the program is running. So their address is valid always. In the main function, I call that function and pass its result directly into cout. And you already know how cout handles strings. So we should see the name of the 7th day of the week. Let's run it and see. In the future, we're going to write lots of functions that return addresses, and you'll also come across many functions like this. Alright, let's keep going. We're going close to the end of the lesson. Not quite there yet, but we're getting close. Let's break down string literals in as much detail as possible. Just a reminder, a string literal is an unnamed constant array filled with characters you write between double quotes. And since it's an array, we can mess with it just like we do with regular arrays. But first, let's look at these two lines. They're different. In the first one, we're creating a constant array and initializing it. In other words, we're making a string on the stack, specifically on the stack. In the second line, we're creating a string literal, which gets stored in static memory, and also creating a pointer to it, which lives on the stack. So this one uses a bit more memory overall. But here's the truth. In the first case, memory for the string literal will also be created, but that's only because you're using that literal in other places, like here for example. If it were used only once, the compiler would just embed the characters directly into the stack array. Moving on, you can get the address of a string literal. That'll also give you a peek at the addresses in static memory. You can also use indexing with a string literal because it's an array. In this case, we'll get the character C. And yep, you can add or subtract integers from a string literal. Yeah, it looks a little sketchy, but it works because the string literal is just the address of its first character. So adding 10 gives you the address of the 10th character from that point. And cout treats all three objects the same. In the first case, we're sending the address of the first element in the array. In the second, we're creating the address stored in the pointer, which is also the first element of the string literal. In the third case, we're again sending the address of the first character of the string literal. So the truth is, we've never actually sent text to cout. We've always sent an address. There's your big reveal. Even though, honestly, we still don't know much about this whole line. We don't know what std is, why there are two colons, what that symbol means, or why we're allowed to write a never-ending string in cout. I'll explain all that if I live to see that beautiful day. Now we're moving on to multidimensional arrays. And just so you know, you can create multidimensional arrays of pointers, but I'm not even gonna show that. That's just straight up madness. Same thing with creating pointers to 3-dimensional arrays or 4-dimensional arrays, and so on. You could figure out how to do it, but honestly, I don't recommend it. It's useless information. But pointers to 2D arrays, now that you might actually run into, because 2D arrays are still kind of common in programming. Let's look at the code. I've got 3 1-dimensional arrays of different size. I only need one pointer to work with all of them. But then I make 3 2-dimensional arrays, and now it's a different story. You can't create one pointer to work with all of them. Why? Because their types are different. So why were we able to use a single pointer for the 1-dimensional arrays? Because we made a pointer to their element, and that's basically just a pointer to a variable, a single variable. Alright, so to create a pointer that works with a 2D array, we need to make a pointer to one of its elements. And what is an element of a 2D array? The answer is a 1D array. For example, our first 2D array is made up of 2 1D arrays. So we need a pointer to a 1D array. Not to a variable, but to a whole 1D array. I've shown you how to do this before. You write the type, just like you do at the start of the 2D array. Then in parentheses, you put the asterisk and the name of the pointer, and then in square brackets, you write how many elements are in one element of the 2D array. So in our first 2D array, each row or element has 3 elements. That means to make a pointer to this array, we use the number 3. Just like I did below, the second 2D array has rows with 6 elements, so I used 6 there. Same logic with 7 for the third array. So now we've got 3 pointers, but you can't use the first pointer to point to the second or third array because their rows are a different size, not 3 but 6 and 7. Now I've created another 2D array. This one has a different number of rows, it has 5 rows, but each row still has 3 elements. That's the same as in the first array, so I can reuse the first pointer for this one. You get it, right? It's all about the second number. The number of rows doesn't matter. It doesn't affect the array's type when creating a pointer to it. As long as the number of columns matches, you can point to it. When you've got a pointer to an array, you can work with it just like you would with a regular 2D array. Like here. I loop through all 5 rows of my fourth 2D array, and inside it, I loop through all 3 elements of each row. I first assign some values, then print them out. Notice how I'm using double indexing with pointers. Why does that work? Because you understand what's going on under the hood. Under the hood, here's what's happening. We take the address of the first element in the entire 2D array, which is the address of the first row, or first 1D array, and we add an offset. At first it's 0, then it's 1, then 2, etc. We dereference that address. What do we get? We get the address of the first number in that row. Then we add another offset, again starting from 0, then 1, and so on. That brings us to the address of the specific number, and we dereference that to get the actual value. This expression is exactly the same as this one, but I think the first one is easier to use. Let's run it and take a look. Now, let's figure out how to pass a 2D array into a function. You probably already guessed. We need a pointer parameter that can hold the first element of the 2D array. And here's the annoying part. You have to specify the number of columns in the array. And yeah, another downside is you can't pass in 2D arrays of any size because the pointer is tied specifically to the number of columns you wrote here. This has to be a number that's known at compile time, so it can be a literal, like it is now, or you could create a global constant and plug that name in both here and here. That way, when you want to change the number of columns, all you have to do is update the constant. You don't have to search the whole codebase for magic numbers. Still, it's kinda clunky. Luckily, there is a way to write a function that works with 2D arrays of any size, but you'll need to allocate them on the heap instead of the stack. Why? You'll find out in the next lesson. You can also write a function template and pass in the array size using angle brackets. But let's not touch templates just yet. It's a huge topic and I'm saving it for way later. I called this function 3 times. I passed in 2 arrays and a pointer. Let's run it and take a look. I don't know if you noticed, but I've actually never shown you how to use a range-based for loop to go through all the elements of a 2D array. I didn't do it because you don't yet have enough background for it to work properly. But you can try to write the following code. In the outer loop, we create a pointer to an element of the 2D array. That means with each iteration, this pointer should point to the next 1D array in the 2D array. And inside, we create a pointer to a variable, which is supposed to go through each element of that 1D array. Then we dereference it to get the value. But as you can see, it doesn't work. The thing is, for this to work, you need to use references, not pointers. That means change the asterisk to an ampersand and remove the asterisk here. Then everything will work fine. But you don't know what references are yet. Don't worry, you'll learn all about them in upcoming lessons. Just hang in there a little longer. Now that we know all this, let's get back to the std_time function. Remember, we use it to get a seed for the std_srand function. But the time function doesn't just return the number of seconds. It can also write that number to the address you pass to it as a parameter. For example, I created a variable called the function, and I can pass the address of my variable to it. The function will write the same number it returns into my variable. So these 2 lines are basically the same. But we're not going to do that. I'm telling you this just so you understand why we passed 0 here. The function expects an address. When I first introduced it, you didn't know what an address was. Now you do. And now you get why there's a 0 here. It's like a placeholder, so the function doesn't write the seconds anywhere, it just returns them. From now on, instead of 0, try to use nullptr because it makes the code clearer. Alright, let's finish up the lesson. I'll explain one more concept. There is something called a dangling pointer. A dangling pointer is a pointer that points to a memory area that's already been freed or is invalid. Using such a pointer leads to undefined behavior, program crashes, errors, or corrupted data. Here's the first example you're already familiar with. In the createDanglingPointer function, a local variable, local var, is created on the stack. After the function ends, local var is destroyed and the memory it occupied becomes invalid. The pointer ptr in main still holds the address of local var, but that address now holds garbage or someone else's data. Dereferencing that pointer is dangerous and causes errors. That's why it becomes a dangling pointer. But more often, pointers become dangling when you work with the heap. You don't know how to allocate memory on the heap yet, but from the previous lesson you heard that you can do it with the new keyword. So check out this example. Here we allocated memory for one variable on the heap and gave it the value 100. The pointer holds the address of that variable. Then I free the memory using the pointer, but the pointer still points to that memory. So if we try to dereference the pointer after freeing the memory, we get undefined behavior. In the future, you'll probably make mistakes and get dangling pointers, but that's part of learning. There are lots of tools in C++ to help avoid this, and we'll study them when the time comes. And now we've come to the main question that's on your mind. Why do we even need pointers in C++? In C++, you often have to work with dynamic memory, the heap, where objects are created and destroyed while the program is running, not statically. For that, you use the new and delete operators, and the result of new is a pointer to the allocated memory block. Pointers let you create objects on the fly, dynamically, when their size and number aren't known beforehand. Also, control the lifetime of these objects, when to create them, when to delete them, and save memory by allocating it only when needed. Passing large data structures or arrays by value into functions, copying them, is very inefficient. It wastes a lot of time and memory. Pointers let you pass the address of objects to functions, not copies. This is faster, only the address is passed, usually 4 or 8 bytes, and allows you to modify data inside the function, since the pointer points to the original. Also in C++, arrays and strings are basically pointers to blocks of memory with elements. Pointers let you move through arrays using pointer arithmetic, like adding the size of the type to get the next element, and work with buffers and data streams of any size. Many data structures, linked lists, trees, graphs, are built using pointers. Nodes in these structures contain pointers to other nodes. Also, pointers let you dynamically change the data structure while the program runs, and pointers provide flexibility and efficiency. C++ is a systems-level language, often used for writing drivers, operating systems, game engines, where direct access to memory and hardware is required. Pointers enable address-oriented programming, working with memory, registers, and hardware buffers, and optimizing speed and resource use. C++ also supports polymorphism. Although polymorphism is implemented using references and pointers, pointers are often used for dynamic binding of objects, storing and passing base and derived type objects, and managing object lifetimes with smart pointers like std unique ptr and std shared ptr. As you already know, pointers can point not only to data but also to functions. This lets you pass functions as arguments to other functions, implement event handlers, callbacks, and strategies. And pointers give you maximum flexibility and control over what happens with memory, allow you to write efficient and fast code, and are often necessary where standard container abstractions like std vector don't fit. You'll constantly encounter and work with pointers in C++. And lastly, why can pointers be dangerous? Pointers are a powerful but also risky tool in C++. They give you full control over memory, but that control comes with a need for great caution. Here are the main reasons pointers can be dangerous. First, accessing invalid memory, dangling pointers. If a pointer still points to a memory that's already been freed or is no longer valid, trying to access data through it leads to undefined behavior. Program crashes, unexpected termination, reading or writing someone else's data, hard to find bugs. Here's an example. You create an object, free its memory with delete, but forget to nullify the pointer. Then try to access it again. Second, memory leaks. If a program allocates memory with new but doesn't free it with delete, that memory remains occupied and unavailable, causing a memory leak. If a pointer is lost, for example, overridden with a new address, you can't get back access to the old memory, leading to increased memory usage and possible program failure. Third, uninitialized pointers. If a pointer is declared but not initialized, it contains a random garbage address. Accessing data through such a pointer is an error. Fourth, buffer overflow and going out of array bounds. Using pointer arithmetic without proper checks can lead to accessing memory beyond the allocated array or buffer, causing memory corruption. Fifth, double free errors. If you free the same memory twice, for example, call delete twice on the same pointer, the program may crash or corrupt data. And sixth, complexity of understanding and maintenance. Code with pointers is harder to read and maintain, especially if pointers are passed into functions and changed during program execution. So, why are these errors dangerous? First, undefined behavior. The program might seem to work fine at first, but can crash unexpectedly, give wrong results, or corrupt data. And what's next? Debugging difficulty. Pointer errors often don't show up immediately, but appear later or under specific conditions. And third, security vulnerabilities. Misuse of pointers is a common source of security issues like buffer overflows or dangling pointer use. So how to reduce the risks? Use smart pointers like std unique ptr, std shared from the standard library. They automatically manage object lifetimes. Initialize pointers right when you declare them. Carefully track who and when frees memory. Avoid manual memory management if you can use containers and standard data structures. And write clean and clear code. So here's the summary. Pointers are dangerous because they give direct access to memory without extra protection or control. Mistakes with pointers lead to leaks, data corruption, crashes, and even security holes. So you have to handle them very carefully and use modern memory management tools. And that's it for this lesson. Thanks for watching. If you liked the video, feel free to hit the like button, leave a comment, subscribe to the channel if you haven't yet, donate via the link in the description, or become a channel sponsor to get access to practical lessons. Goodbye.